Okay, we're going to be looking at some trig functions right now. In fact, we're going to be looking at inverse trig functions. But I wanted just to start off refamiliarizing each of you with some important trig identities that you looked at in pre-calculus, the double angle formulae. These identities, ideally, you might have committed to your memory, but if you don't have them embedded in your head, at least know that they exist, so that when you are doing problems and you see something like sine of 2 theta, you know that you could re-express that in some other way, and you know that you could, look in a textbook or on the internet and find out what that double angle formula is, because throughout the next problem set and sets, you will be doing some work with these. Okay, but let's get into trig functions and a slight review of them. First thing, are trig functions one-to-one? In other words, for every x, there's one y, and for every y, there is one x. Well, we know that that's not true. Here's sine of x. And if we were to draw a horizontal line, we see that it fails the one-to-one test, because for this given value of y, there's a number of values of x. But what does that tell us? If it's not one-to-one, that means that the inverse function, or the inverse, is not a function. But what we want to do is force them to be a function. We want to force them to be one-to-one. So the idea is that you can take our function sine of x and cut it off at a point. So we could cut it off here at negative pi over 2 and here at pi over 2. And if we look at the domain from negative pi over 2 to pi over 2, on that given domain, it is a one-to-one function. Therefore, we write that the inverse function, sine inverse of x, which is equivalent to arc sine of x, will have the domain negative 1 to 1 and the range from negative pi over 2 to pi over 2. So we are denoting this chunk of sine of x that is 1 to 1. We write that as capital S of x, that's on the interval from negative pi over 2 to pi over 2. And so sine of x, big sine of x, this, which is our regular sine of x on that interval. So our big sine of x does have a one-to-one relationship. And therefore, it has an inverse. And the inverse, as I said, is that. So here's a graph of arc sine of x. This is all review for you. That's the domain. This is the range. Similarly, we can talk about arc cosine and arc tan. But before we do that, let's just think about what arc sine means. So what this is saying, and to rewrite that in more helpful notation, 0.707 is root 2 over 2. This is saying what angle, or rather, sine of what will give me root 2 over 2? Well, we know that that is pi over 4. So this equals pi over 4. Let's look at this one because here we have to consider our domain. So our domain, going back, is that we're only looking between -1 and 1. So for arc sine of -√3/2, that's saying sine of what will get me -√3/2. Well, if we think about that, here's our graph, here's sine, and we're just looking at this portion of our graph. So that's down here, and that would be -pi/3. So sine inverse of -√3/2 equals -pi/3. Okay, so that's just a review of evaluating inverse trig functions. Um, and what we want to do is now start considering what they mean geometrically. So let's think about simplifying this. Well, we can say, if arc sine of x is saying sine of what number y will get you x. Well, I've drawn the triangle here, and this is a helpful thing for us to do for what we're leading up to. So here's my angle y, and we know that opposite over adjacent must be x. So, sorry, opposite over hypotenuse. So we say this is x and this is 1. Using Pythagorean theorem, we know that this is 1 minus x squared. Therefore, cosine of this value, or of this angle, because remember, this here equals y, where y is an angle. So we can replace this with cosine of y, which is 1 minus x squared over 1. All right, more problems, more review. Uh, so now we want to use this idea to find the derivative of arc sine. Well, remember, since if y equals arc sine of x, and we want to find the derivative of arc sine of x, what we do is we draw a triangle, and we say, okay, we know that sine of y must equal x. So this is y, this is x, and 1, and 1 minus x squared. So then what we do is we're going to use implicit differentiation. We know sine of y equals x, and we're going to take the derivative of both sides. So the derivative of the left side becomes cosine of y times dy dx equals 1. And then we can solve for dy dx. And then using this relationship that we just found, this triangle, we know that cosine of y is just root 1 minus x squared over 1. And therefore, we just developed the derivative of arc sine of x. The derivative of arc sine of x equals 1 over the square root of 1 minus x squared. And we use our understanding of right angle trigonometry to develop that. Okay, so let's just do some chain rule, some hard problems with arc sine. So we know that we just developed that the derivative of arc sine of x is 1 over the square root of 1 minus x squared. So using the chain rule, the derivative of this would equal 1 over the square root of 1 minus the inside, 1 minus x squared, times the derivative of the inside. Well, that's, if we re-express this as 1 minus x to the 1/2, then we get 1/2 1 minus x to the negative 1/2 times the derivative of the inside, which is -1. Okay, let's simplify this. Well, this equals 1 over the square root of 1 minus x, because the squared and the square root will cancel itself out, times, now writing this all in the proper place, -1 over 2 times the square root of 1 minus x. Delving into this a little bit further, we get that this equals -1 over the square root of negative x, sorry, of x, times 2 times the square root of 1 minus x. And there we have the derivative using this chain rule. It's a little bit ugly, but rewriting this in just a little bit nicer terms, we have 2 times root x times 1 minus x. Okay, let's proceed a little bit further. What about this problem? Well, we can use a u substitution. Let's let u equal x squared. So du dx equals 2x. Du equals 2x dx. So we can rewrite this as 1 du over square root of 1 minus u squared. Well, this equals arc sine of u plus c. And now we just substitute our value in, and we get arc sine of x squared plus c. Okay, so that's dealing with arc sine. Now let's talk about cosine. Well, just like we had big sine of x, we can have big cosine of x, and we want to force that to be 1-to-1. So that's 1-to-1 on this interval between 0 to pi, and my y values are going from -1 to 1. So on that range, or rather on that domain, we have a 1-to-1 ratio. So then we can start talking about arc cosine of x, or cos inverse. And cos inverse, similar but slightly different. Its y values go from 0 to pi, and that's because from a unit circle, from 0 to pi goes through all of the cosine values. And my x values are ranging from -1 to 1. And if we think about the derivative of our cosine, I've written it right here, but let's develop it. So if we have y equals our cosine of x, the development is really just the same. What we do is we say, well, this is x equals cos of y, so this is y, and this is x and 1, and this must be 1 minus x squared using Pythagorean theorem and what we know about trig functions. So now if we take this and take the derivative of both sides, we get 1 equals negative sine of y times dy dx. So dy dx equals -1 over sine of y. Well, sine of y is opposite of our hypotenuse. So dy dx equals -1 over root 1 minus x squared. And that's our derivative. And again, we can only talk about that derivative on the range between -1 and 1. for two reasons. One, because that's the domain of arc cosine, and two, because if I were to plug any numbers outside of that range, I would be square rooting a negative number, which we know we can't do. So let's evaluate this definite integral. We look at this and we say, oh, it's got a negative value there. So therefore, this equals the arc cosine of x evaluated from 0 to 1/2. So that would be arc cosine of 1/2 minus arc cosine of 0. And now we really need to test our trig understanding. So arc cosine of 1/2, that is pi over 3. And arc cosine of 0, well, that's pi over 2. Just as a reminder, because cos of pi over 3 equals 1/2, and cos of pi over 2 equals 0. So simplifying this, we have 3 pi over 6 minus, sorry, 2 pi over 6 minus 3 pi over 6, which is negative pi over 6. Okay, last trig function that we're going to look at is tangent. So here's tangent. Now, regular tan continues to go like this. Oops. But we want to look at a one-to-one function. So we're looking at big tan of x, which goes between negative pi over 2 and pi over 2. Therefore, the arc tan of x will look like this. It's going to have asymptotes at pi over 2 and negative pi over 2, and the graph looks like that. So the domain of arctan is all real numbers, and the range is between negative pi over 2 and pi over 2. So if we develop the derivative for arctan using the same kind of methods that we've been using, we say that tan of y equals x. So therefore, we can create our triangle where this is angle y, x over 1. So this must be square root of 1 plus x squared. So if we take the derivative of this, we get secant squared of y times dy dx equals 1. Solving dy dx equals 1 over secant squared of y, which equals cosine squared of y. That's what dy dx is. Well, if we cosine squared of y is 1 over 1 plus x squared squared, which is just 1 over 1 plus x squared. Tangent, derivative of arctangent of x. This is the derivative here of arctan of x. So now we're finding dy dx at the following point if y equals arctan of x squared minus 2. So we use our rules. We know that the derivative of arctan equals 1 over 1 plus x squared. So using the chain rule, dy dx equals 1 over 1 plus x squared minus 2 squared times the derivative of the inside times 2x. Okay, well, now we plug in our values. So dy dx equals 1 over 1 plus 1 squared minus 2 squared times 2 times 1. And this ends up equaling 1, if you simplify that nicely. Okay, so now let's deal with an integration problem. So we look at this and we say, okay, well, this doesn't look exactly like what we've done, but we've got no square root here, and there's no square root, and it's 1 plus something being kind of squared. Well, let's toy with some things. So let's let u equal x squared, and if we do that, then we get du dx equals 2x, du equals 2x dx, and that's almost this. So if I threw a 1/2 and a 1/2 there, now it's exactly that. So we could rewrite this as 0 to 1. Well, let's actually do this really properly. So we're going to go um, 1/2 du over 1 plus u squared. And we're going to change these limits in terms of u. So we're going to say u equals, well, when x equals 0, u equals 0 squared, which is 0. And when x equals 1, u equals 1 squared, which equals 1. So now we have this entirely in u. It actually didn't change the limits, but we can be convinced that we're doing it right. And so this equals 1/2 the integral from 0 to 1 of 1 over 1 plus u squared du. And we know now that that's tangent. So for arctangent. So we get that this equals 1/2 arctan of u evaluated from 0 to 1. Well, this is 1/2 arctan of 1 minus arctan of 0. And give myself a little bit more space here. Uh, so this equals 1/2. Well, arctan of 1 is saying what angle gives you tan of 1, and we know that that is pi over 4. And arctan of 0 says tan of what angle gets me 0, and we know that that is 0. So this equals pi over 8. Okay, so this is just a review of the critical ideas that you should be familiar with after this. First of all, here are the derivatives of the 3 trig functions you should know, and here are the antiderivatives of the trig functions you should know. And you really only need to know the, the integral of this in terms of arc sine of x, because they're only off by a negative sign. So you could always just pull out a negative and force it to be arc sine. I think that's all we have for today. Oh no. So one more problem. It says solve this by completing the square. Well, this is a nice challenging problem. If we complete the square for this is a good technique for integration. What we could do is we could write this as 1 over x squared plus 6x plus 9 plus 4. Okay, we split the 13 into 9 and 4 because now we can write that as the integral of 1 over x plus 3 squared plus 4. Okay. I need to make this look like one of my trig functions. So I know that the integral of 1 over 1 plus x squared dx is arctan of x. This is the one that looks most like it. So what if I divided everything by 4? And I'm dividing everything by 4 so that I can turn this 4 into a 1. Let me get rid of that. So this equals, if I divide everything by 4, 1/4 over x plus 3 squared over 4 plus 1 dx. Further simplifying that, I could write this as 1/4 the integral of 1 over 1 plus x plus 3 over 2 squared. And I'm writing that so that now the entire thing is squared. I've embedded the 4 here inside, square rooting it to make it a 2, but now it's part of the squared dx. Okay, well now we do a u substitution. Let u equal x plus 3 over 2. And if we do that, du dx just equals 1/2. So du equals 1/2 dx. Therefore, 2 du equals dx. And now let's do a little bit of work on the next page so that we can actually see what's going on here. Okay, so we could rewrite this all now as 1/4 the integral of 1 over 1 plus u squared. And now plugging this in for dx, we get 2 du. Furthermore, we can bring the 2 out. We get 2/4 the integral of 1 over 1 plus u squared du, which equals 1/2 arctan of u plus c. And last step, just substitute in for the u, we have 1/2 arctan x plus 3 over 2 plus c. This is just an example of a challenging integration problem where you need to use a bunch of previous algebra techniques to force our integration to fall into one of our arctan or arctrig functions. So to summarize, let us go back to that previous page and let's leave it at that, which is that these are the things that you need to know. The derivative of arcsine, arccosine, and arctan, and then the integral of the following. But remember, if you are to ever forget which these are, you can redevelop them. So just as a quick redevelopment, if I have arc sine of x equal y, and I want to find the derivative, we create a triangle, and we say, well, sine of y equals x, so this must be x over 1. Therefore, this is 1 minus x squared rooted. And then we take the derivative. And then we solve. So y prime is 1 over cos of y, which equals 1 over 1 minus x squared. So these derivatives are pretty elegant in that they're all embedded in some nice, fun trig relationships. Okie dokie, that's it.